In this problem, we're asked to find the final speed of a falling mass in this horizontal Atwood machine, but the pulley is now heavy, so we can't just say, oh, it's a light pulley and I can ignore what's going on with that. We actually solved this problem previously by using energy conservation, and I'll just post a link to that real quick. Now we're taking the approach of using forces and torques and the acceleration of the system in order to solve this question of how fast is that mass moving after it's fallen by 40 centimeters. So we can start to get some force vectors into the graph. And I'm going to go ahead and work with the second graph because there's just a little more room to put vectors in. So that mass is being pulled on with a tension of T1. And my hanging mass is being pulled on by a string also. And one key difference with a heavy pulley is that these two tensions are no longer the same. In fact, they're necessarily different from each other. And the reason why is I need to have a net torque on that disc pulley to get it to accelerate. So if I look at the tension exerted on the pulley by T2, here's that. That's going to create a clockwise torque. Now it's coming off the pulley tangentially, so that's automatically perpendicular to the radius. There's my radius, and that's the lever arm for the torque. So the clockwise torque exerted by T2 is going to be a T2 multiplied by the radius. And I'll write that down in a minute. T1 is also pulling on that pulley, and it's exerting a counterclockwise torque of T1 times the radius of the pulley. So the net torque on the pulley is what causes it to start to spin up. To finish things out in my force diagram, I have the force of gravity down on the hanging mass. I'm just going to give that a name and call it M2G, and we'll go ahead and call the other mass M1 in case we need to refer to them symbolically. And I'll go ahead and put a number on M2G. That was half a kilogram times 9.8. Might be convenient to have that later. So that's 4.9 newtons pulling downward. The next thing I'm going to do is put the direction of acceleration in next to every moving piece here. And we're going to use the actual acceleration direction as the positive direction for the analysis of each piece. So that mass is accelerating to the right. The hanging mass is accelerating down. I'm going to call that the positive direction for the analysis of that piece. This is going to make it so A is positive for each of those masses when we get to where we're doing the algebra. And then the disk, well, this is kind of a new thing. It's not accelerating, it has an angular acceleration instead, so it's twisting. And I'm going to call that the positive direction. So that's clockwise for the positive direction, which means the torque exerted by T2 is going to be a positive torque. And then T1 is trying to slow this thing down. It's exerting a counterclockwise torque, and that's going to count as negative. So I think we're ready to start writing down equations for each of the moving pieces. We'll do M1 first. And I apply Newton's second law. I go F net equals MA. And the net force on it, well, T1 is the only thing pulling horizontally. So I have T1. And then M1, I'll leave like that for a second. And then I'm going to go ahead and put in numbers so that I'm preparing to do my algebra. So T1 is M1A. Well, M1 is just 1. So T1 equals A. There's my first useful equation. Next, I move on to M2, and I apply Newton's second law to that. And the net force on M2 is going to be M2G. Again, that's the positive direction for the analysis because it's actually accelerating that way. Minus T2 equals M2A. And then I clean it up to get ready to do my algebra. And M2 is 0.5. And M2G, I've already computed as 4.9 minus T2 is equal to M2A. And again, M2 is 0.5 kilograms, so 0.5A. There's my second equation in the system. Finally, I do the disk. And now instead of saying Newton's second law, F net equals MA, I use the rotational analog to that. The net torque is equal to the moment of inertia of this thing times the angular acceleration. So my net torque is going to be, again, T2 times the size of the lever arm, R, clockwise, minus T1 times the size of the lever arm, counterclockwise. The moment of inertia of a disk is 1/2 mr squared, and the angular acceleration is left in there symbolically. So one thing I can do real quick is cancel one factor of r from both sides of that equation. But then I need to go and think about what's the relationship between the acceleration of this mass and the angular acceleration of that disk. And the argument goes like this. The string cannot stretch. So the acceleration of the mass has to be equal to the acceleration of the string at every point along the string, including where the string is coming off of the pulley. It's going to have an acceleration of a there equal to the acceleration of the mass. But if the string can't slip on the pulley, which it's not allowed to do in this problem, that means the tangential acceleration at the edge of the pulley is equal to the exact same a. And we have an equation relating the tangential acceleration at the edge to the angular acceleration, and that allows me to substitute for that alpha. Again, the tangential acceleration is equal to that linear acceleration of the mass, so just a over r. So let's get that subbed in, and I get t2 minus t1 is equal to 1/2 mr times a over r, and another factor of r is going to cancel. So finally, I can just put in numbers and get ready to do some algebra. So I have t2 minus t1 is 1/2 m, where m is the mass of the disk. Well, that was 1 kilogram, so I get 0.5 times a, and I have my third equation for the system. Now I'm ready to tackle the algebra part of the problem. This is a system of 3 equations and 3 unknowns. The unknowns are the 2 tensions and the acceleration. All I care about for this particular problem is the acceleration, because I'm trying to predict what's the speed going to be after the mass is dropped through a distance of 40 centimeters. So I'm going to try to, as quickly as possible, solve for a. And it looks to me like a good move would be to substitute a for t1 in the third equation. So the first equation says t1 is just a. So I'm going to write down t2 minus t1, but that's just a, is equal to 0.5 a. Then when I look at my middle equation, that was 4.9 minus t2 equals 0.5 a. And I realize that if I add these two things, the t2 is going to eliminate, and I'm left with 4.9 minus a equals a. In other words, 2a equals 4.9. And I end up with a equals 2.45 meters per second squared. Now that I know the acceleration of the problem, I have a kinematics question. And I don't have to fuss around with worrying about the direction of plus or minus for my coordinate system. I'm just treating it like, okay, this mass is going to start at 0. It's going to end at 0.4 meters, and it starts from rest, and I'm going to call the acceleration positive. And I should be able to find the velocity at the end of that process. So I'm going to use the kinematics equation, v squared equals v naught squared plus 2a times x minus x naught. And I'm calling the initial location 0. And it started from rest, so v naught is 0. So very quickly here I get that v final is going to be the square root of 2a times x final. So that's the square root of 2 times 2.45 times 0.4. And I end up with 1.40 meters per second for the final speed of that mass. And that's the same value that we got by using energy in that previous video.